So up to this point, we've looked at equilibrium constant expressions using concentration. But sometimes you work with gases, it might be more convenient to measure the pressure instead of the concentration of the gas. And it'd be nice if we could do an equilibrium constant that involved pressure terms instead of concentrations. In fact, we can. And that's because there's a relationship between pressure and concentration. You remember from the ideal gas law that there's a relationship between these two. So here's an example. This is the same reaction we had in a previous video, where we have nitrogen gas and hydrogen gas reacting with each other to form ammonia gas. Okay? We know PV equals nRT. That's one thing we know, right? And if we rearrange this a little bit, we can get P is equal to N over V. N is moles, V is volume, moles over volume is concentration. We'll call that C. Okay, so pressure is equal to concentration of the gas times R times T, so the concentration is equal to P over RT. So using the ideal gas law, there is a relationship. There is a relationship between concentration and pressure, and it's by this factor of 1 over RT. Okay, so if my K value is the concentration of NH3 squared over concentration of N2 to the first power times concentration of H2 to the third power, and I replace the concentration concept from brackets, we just go to C. Concentration of NH3 squared, concentration of N2, concentration of H2 to the third power. That's the Kc, we call that, the equilibrium constant at concentration. Well, what if I now replace all of those C's with P over RT, where P is the partial pressure of each gas? Okay, it looks unwieldy, but let's make it a little more simple. So Kc, we're going to replace our concentrations, our C, with P over RT. So we have the partial pressure of NH3 over RT squared over partial pressure of N2 over RT times partial pressure of H2 over RT, all to the third power. I factor out the common factor in all of those, which is 1 over RT to some power. So I get P NH3 squared over Pn2 times Ph2 to the third power, and I factor out from each one of those 1 over RT times whatever the exponent is. So 1 over RT squared over 1 over RT times 1 over RT to the third, or 1 over RT to the fourth. And if I do a little bit of algebra on that, Kc now can be represented by Kp. Kp is the equilibrium constant using pressures. It's this partial pressure of NH3 squared over partial pressure of N2 times partial pressure of H2 cubed times, and just do a little bit of algebra over there, you get RT squared. Okay? Now, the square part of this, because of where it came from, the RT squared, the exponent of RT, is dependent on the reaction that we've actually used, because the coefficients come from, or the exponents come from the coefficients. So if my reaction's different, then my exponent for RT is going to be different. There's an easy general way of looking at it. We'll talk about it in a second. Okay? So Kp is equal to Kc, and then RT, if the coefficients are the same on both sides, you can cancel out your RT term. Again, because the exponent of RT comes from the coefficients of the reaction. So in general, we say that Kp is equal to Kc times RT to the delta N. Okay, where delta N is the difference in number of moles of gas on either side of the equation. It's the number of moles of gases on the product side minus the number of moles of gases on the reactant side. So for our reaction, right, delta N, L plus M minus J plus K. For the specific reaction that we had here, we had 2 for the ammonia minus the sum of 1 and 3 for the reactants, and 2 minus 4 is minus 2. So delta N would be minus 2 for this reaction if you wanted to find Kp from Kc. Now remember, in the previous slide we saw that Kc was equal to Kp times RT to the second power, not the negative second power, but look at the difference between these two. One is calculating Kp, relating Kp to Kc, and the other one is relating Kc to Kp. So the overall rule here is if you're going from Kp to Kc, it's Kp equals Kc times RT to delta N. And if you're going from Kc to Kp, it's Kc equals Kp times RT to the negative delta N, the opposite sign, because it's found in a different way. It's found by the relationship is different algebraically. Okay? So here's an example. Set up the expression for Kp in terms of Kc, R, and T. There's our thing. So delta N is going to be 2 for NaCl minus 2 plus 1, or 3 minus 1. So Kp is equal to Kc times RT to the minus 1. And if you just put that in, anything to the minus 1 is 1 over. So Kp is equal to Kc over RT, or Kc times 1 over RT, Kc over RT, for this reaction. Again, because delta N changes depending on the coefficients in your reaction. Okay? So Kp and Kc are fairly useful. If you're given pressures, use Kp. If you're given concentrations, use Kc. If you're given a mixture, you can kind of decide, and depending on which K value you're given, you can convert it into the other using that, Kp equals Kc times RT to the delta N, or vice versa. And you have a little bit of freedom now and a little bit more tools in the toolbox to solve some of these problems.